Good morning, good afternoon, and good evening, everyone. So, today we're going to be continuing our linear algebra series, and we're going to talk about inverses. And so, here's the bottom line idea of what we're going to be doing it's this idea of how do we reverse a linear transformation. Okay? For first of all, we're going to apply linear transformation to encode a vector. So, we're thinking about this idea of encoding and decoding something, right? So given a vector, when we transform it, it's going to be a new vector, right? So for instance, say we have this t as our transformation, and we input some vector x, which is the same thing as a mat vec. So we're multiplying a matrix A by x, where A has, let's say, these entries, and yeah, we're going to get some transformation out of this, depending on what the linear transformation is. Okay? And so here we say, okay, this is linear, such that if we have, let's say, a set of two vectors, we apply linear transformation to both of those vectors, and we're going to get a vector out of it. And so actually, we use this transformation right here. That's the transformation we use. How exactly? So if we remember, these are just technically functions, right? So let me just do this. Here's how it would look like. Let's say we have that. Okay, and so we're multiplying a matrix by some vector with three components. I'm going to say they're x sub 1 to 3. This is the same thing as saying, oh, actually, so if we try plugging in 12, 9, and 4 here to these guys, we're going to get, so we transform them, we're going to get this one. And same idea for the others. Okay, but the idea is that this is the same thing as writing this guy, which is the linear transformation, which is essentially just multiplying a and x together. So it's going to look like x sub 1 plus 3x sub 2 plus 2x sub 3. And then we also have negative 2x sub 1. So here I'm just noting down the coefficients as long as with the variables. 2x sub 1 plus 6x sub 2 plus 5x sub 3. So whatever x sub 1 to 3 we plug in here, we're going to get a vector out of it. So if we plug in 12, 9, and 4 to this transformation, we're going to get a vector out of it. And same goes with 5, 1, 8. Okay, cool. So here's the thing. It's not good enough to encode a message if it cannot be decoded, right? Why would you give someone a message that's encoded, but that receiver cannot even decipher what that message is? And so to see how we decode, suppose we have encoded this vector here. It's encoded. So we say this is an encoded message or vector. Okay. And we need to find vector x such that, right, this input vector x that we plugged into our linear transformation, which is the same thing as multiplying it by some matrix A, which is equal to y. I forgot to do this. And so, okay, we have this linear system, right? We got it from here. And so we just equate it to the output vector 109, 995, 241. And then if we use Gaussian elimination, we're going to get this solution. And so it's only one solution. And so my x vector is going to have these components. So the idea is in order to solve for this x, we have computed the inverse of t. So actually, it's pretty easy, right? Because we've been doing Gaussian elimination countless times. So we're just trying to say it in a more compact way that, oh, we're actually computing the inverse of the transformation. And so, okay, if we transform it so we say the inverse of y, we're going to get back the input x. Okay. And so a funny thing, well, at least what I would say is if we compute, so here we can extrapolate the idea. If we compute the inverse of the transformation of our input, that's actually just that same vector. Okay. Right. Now to find the general formula for this inverse, so we do y sub 1, 2, and 3. Okay. And so we just find out what the solutions are for x sub 1, 2, and 3. And we're going to get this. This is basically the solution that we get. And we could translate that into a vector. So here we just get the coefficients of each equation. Oh, this one's -1. +6, -2. Now we have a 0 somewhere. There we go. There's the 0. So we just get their coefficients. We store them in a B matrix, and we should be able to get B multiplied by that output vector to get X. Okay. Now we talk about inverse linear transformations. So let's talk about that real quick. So inverse linear transformations. Okay, I'm actually looking at my textbook. So, oops, whoopsies. Give me a second. So say we have this linear transformation E, and we put in some vector that has m components, and we get an output vector of n components. And we say this is 1-to-1. So we know what a 1-to-1 linear transformation is, right? Basically means we input some vector, we're going to get a unique vector out of it. And those are the only connection that they have. It's kind of like a function, right? So actually, here's the definition of 1-to-1. So it pairs, so just a brief review from the previous section, it pairs up to each vector x, so each vector x in our M with unique vector y in Rn. And so what does that mean? It means that the inverse, which we denote as t-1, actually creates the same pairing. But in reverse. So what this means is it pairs up to y in Rn with unique vector x in Rm. So it's just the reverse. Okay. So mathematically, the inverse of this y vector is the x vector. So we actually have a nice figure here that can I copy this? Oh no, it's not copy. Whoops. So I can't copy it. I can just take a screenshot. I'm gonna do that. So here's what it would look like. There. So what this is saying is, right, we start with p of x, we get an output y. And then we can, oh, actually, oh, this is x, this is y. Okay, so we can transform x to a y and vice versa. We transform y back to x. And we get into its inverse linear transformation. So it's really the same as functions, but we just use it for vectors, right? Okay, let's look at the definition. My least favorite thing to look at. So this definition tells us that we actually have some buzzwords here. And these buzzwords are very similar to each other, such that, no, I'm not going to say such that. They are the same. So say we have this linear transformation. We're going to denote it as t. We always denote it as t. We get a vector from Rm, and it goes to Rn. And we say that this linear transformation is invertible if, okay, here's the catch, t is 1-to-1, and onto. So we already know what 1-to-1 is, but to briefly review, what is onto? If we look back at the previous section, we're gonna find what that means. Or I could just look at my previous video. I actually made this nice table here. If it's onto, we have some characteristics to tell that this is onto. So we say that if we have an augmented matrix, so you know how that linear transformation could be converted to a matvec, and so that matrix in that matvec, say is an echelon form, then if we have a pivot in every row, we know it's onto. And if the span of the columns of that matrix is equal to Rk, and the range of that P is in Rk, so range just meaning the images of the vectors, say U, the images of those vectors under T, the range of that is Rk. Okay. I hope that makes sense. Okay, cool. Oh, yeah, and the range is equal to the span because they're both Rk. So lots and lots of buzzwords here, but we'll get through it. Okay, so right, we have. Wait, where was I? Oh, I lost it. Oh, there we go. So what do we say went on to? And there's lots of ways we can define it in terms of characteristics. Okay. So when t is invertible, the inverse function t to the power of -1, which just goes back from Rn to Rm. So I'm gonna write that out. So when t is invertible, the inverse function, so it's actually still a function, say that t with a -1, and this transforms a vector from Rn back to Rm. So it's really just the reverse. And this is defined by the following mathematically. It would look something like, and we've seen it, the t inverse, this output vector y, which is now going to be our input. We say that's x, the x vector, and this original idea where we plug in that input vector in that linear transformation, and then we get back the y. Now, the funny thing, and I think I've mentioned this, we can say that if we transform the inverse of y, we're going to get back that y. Okay. If we transform, this thing is just x, and t of x is just y. So I'm basing these ideas from the two. And what else do we have? If we do the inverse of x, that's still x, right? Because t of x is this y, and then we just plug it into the inverse, we still get back our x. Okay. So that's what that idea is. Okay. I hope that makes sense. I'm just trying to read through what's the next thing I'm going to say. So in our secret code example, the encoding linear transformation mapped vectors in R3 to other vectors in R3. So in our previous example, right, we input some x vector that has three components. So it's a three-dimensional vector. And our output is still a three-dimensional vector. And we observed that the inverse for the coding was another linear transformation. So I mean, it's pretty simple, right? In algebra, no, not even in algebra. In pre-calculus, or okay, algebra. If we're given a function, we input some real number in there, and we're gonna get a real number out of it, right? And then if that output real number, we plug it into the inverse, and then we're gonna get the original thing back, the original real number. And it's the same idea here, but this time it's for vectors. Okay, cool. Now, this next theorem gives a required condition for a linear transformation to be invertible and tells us that the inverse of a linear transformation is also a linear transformation. Okay, let's just look at this theorem. I think this might be super easy. Let me just write it out. So this is theorem 3.21. It tells us that here we let t be r m to n. And this t is, we already know it's a linear transformation. We're just trying to be mathematically precise about it. So this thing's a linear transformation. And then we have the following. So we say the only way, and this is key, the only way t has an inverse and this is really, really important, is if m is n. They have to have the same number of components, apparently. If they have a different number of components, then we know there's no inverse for t. T. If we say that t is invertible, or it has the inverse, then we say that this t inverse is also a linear transformation. Okay. Cool. Now there's a proof out of this. Yeah, there was so many proofs before. I got bombarded. Do I go through the proof? I'm thinking if I should go through it. Okay, you know what? Fine, I'll go through it. So there was this proof, right? In theorem 3.6 in section 3.1. I wonder where that is. We're gonna go to oh, lagging. I'm not lagging anymore. Actually, I'm a bit. Also, my face looks yellow for some reason because of the lighting. Okay, let me. Where are you? Is this you? No, this is section. hmm, That's 2.3. 3 point. What was it? 3.1. Theorem 3.6. Where is that? Took note of all the theorems, but it's just funny. Okay, we let A be n by m, T is m to n. Oh, and then we define it like this. Is one-to-one if columns of A are linearly independent. So that means there's a pivot position every column. Oh, A and B are the same. Ooh, okay. If n is less than m, T is not one-to-one. And I think I know why. So if m is greater than n, let's say R3 becomes R2. There's going to be some free variable out there. Okay. If we can only plug in two things, there is one free variable somewhere. So we know that's not one-to-one because there's a spare thing. Okay, so that was the theorem there. So here's the proof. T can be one-to-one if n is greater than or equal to m, but n cannot be less than m. And there's another theorem that tells us the only way that T can be onto is if it's the same thing. So it's one-to-one if n is greater than m, and onto if n is also greater than or equal to m. Okay? And so the only way T can be one-to-one and onto, because we need it to be one-to-one and onto for it to have an inverse. Wait, was that? Wasn't the definition. Oh, if it's one-to-one and it's onto. Is if they're equal, m is n. Why not greater? That's what it says so. It only has an inverse if m is equal to n, not if n is greater than m or m is less than n, right? So that's the only way. Okay, we know that. Good. Now for b, this b argument here, if t is invertible, then it should have a linear transformation. The inverse should have a linear transformation. So here we're gonna let y sub 1, I guess, and y sub 2. These are in Rn. Now, if t is invertible, then we know T is onto. And what does it mean for T to be onto? There exist vectors x sub 1 and x sub 2 in Rn. Okay. Okay, actually, I'm going to be honest. I forgot what the definition of onto is. But I think it went something like, I'm kidding, I forgot. There we go. Here's the definition. Oh, okay, so I wrote that T is 1-to-1 if for every W, there exists at most one vector U. And if it's onto, there exists at least one. So here at least, and here at most. So there could be tons of U's that would give me this W if it's onto. If it's 1-to-1, it's only that U. Okay. Okay. All right, let me just complete this proof and we'll take a short break. So, right, we say, so there exists vectors x sub 1 and x sub 2 in Rn such that this T of x sub 1 gives us this y vector y sub 1, and vice versa. This dx sub 2 gives us this y sub 2. Hence, we have the following. We say that t negative 1, y sub 1 added to y sub 2 is going to be equal to, okay, this one's going to be a little bit tricky, the inverse of the sum of the linear transformations of these guys. When we sum these two, this is the same thing as y sub 1 plus y sub 2, right? We just turned them into the linear transformations. And then continuing on from there, we could say, since they are, this whole thing is a linear transformation, there's this property where we can just add these two things and they would be the same thing, right? Then remember that these inverses cancel out, so we would still get that same output. And then we could rewrite this x sub 1 and x sub 2 as the linear transformations of these guys. We could have done all of that without even doing this, because there's that linear transformation property where we could literally separate these two like this. We could go from this step to this step. That's fine. Yes, there's a similar argument that can be shown using a scalar. But here we say that since this works to here, and that is a property of what a linear transformation is, we say that this inverse is indeed a linear transformation based on the other definitions that we know. Okay, hope you guys enjoyed, and I'll see you all in the next video.